Chapter 9 Digital Filter Structures. In this chapter, after introducing various conventional structures, some implementation details of FIR and IIR filters is checked using hardware with limited accuracy. Right. After this chapter, you should be able to quantize filter coefficients for use in hardware integer, control the effect of quantized coefficients on the impulse response, and convert an IIR transfer function into cascade or parallel hardware implementations. Important topic. Now, FIR and IIR structures. From a theoretical point of view, as long as the conversion functions of the structures are equal, there is no difference between their selection. While choosing a suitable structure for a practical point of view depends on parameters such as computing requirements and internal memory, the effects of presenting numbers with limited accuracy, and the area of the chip. The power consumption depends on a VLSI technology and other parameters. Famous structures used to realize FIR filters are direct or direct form or transversal form, frequency sampling, fast convolution, lattice. Now, the structure used to realize IIR filters are direct form, cascade, parallel, and lattice form. Now, suppose the goal is to provide a suitable structure for a quadratic IIR filter as shown below. A0, of course, A0 we have reported it earlier. It's better to be equal to 1. Anyhow, A0 y of n plus A1 y of n minus 1 plus A2 times y of n minus 2 is equal to B0 x of n plus B1 x of n minus 1 plus B2 times x of n minus 2. Okay? Its transfer function can be divided into the following two parts. H of z, which is equal to B0 plus B1z minus 1 plus B2z minus 2 over A0 plus A1z minus 1 plus A2z minus 2 is equal to H1 times H2, where H1 is B0, okay, numerator, plus B1z minus 1 plus B2z minus 2, and this next part, H2, is equal to 1 over denominator, okay, A0 plus A1z minus 1 plus A2z minus 2. Most of the time, A0 is chosen to be 1 because otherwise it's possible to make the coefficient A0 equal to 1 by dividing the sides of equation 9.2, okay? Direct form 1 structure. Direct form 1 structure for IIR filter of degree 2 is illustrated in figure 9.1. Delay is represented by D in the figure, which is equivalent to z minus 1 in a z domain. If all coefficients related to delayed outputs, that is AK, where k is greater than 0, are equal to 0, the above structure belongs to an FIR filter. This issue is also true for 3 other consecutive structures that will be discussed later. Right. Input being multiplied by B0 in this branch, a delay for it, so the name will be x of n minus 1 multiplied by B1, and the last delay will cause x of n minus 2 and multiplied by b2 based on difference equation. And here, just imagine it's written to be equal to 1. The output facing a delay, so the name in this node will be y of n minus 1, will be multiplied by minus a1 and will be added to the rest, and another delay, so y of n minus 2 multiplied by minus a2, and summation here appears. They all make the output which is called y of n. Here you see summations, okay? Now, direct form 2 structure. We can change the location of two boxes appeared here, okay? X of n will be as input to the first box, which is called h1 of z, and the second box as h2 of z. Second box, okay? Second filter, second transfer function. Now, based on the property of LTI system, we can swap the location of h2 with h1. So, we would like to have h2 appearing at first and then h1. So, as the system is LTI, it's possible. Okay? Now, we see here delay, the same node delay. So, the second delay is redundant. We can preserve one of delays as appeared here. We have called this node as wn. So, delay, okay, delay, another delay, the same node. It can be summarized as delay, two delays, minus a1, plus b1, minus a2, and plus b2. Now, an intermediate variable has just appeared, which is denoted as w of n. Okay? The structure is called direct form 2 for IIR filter. Direct form 2 structure for IIR filter, of course for degree 2, is depicted in figure 9.2 as shown. Part A of the figure shows that the place of h1 of z and h2 of z can be swapped to reach to part B. Part C is also a summary of part B. Another name is canonical structure. Why? Because where the number of delay lines is equal to the degree of the filter. Okay? For direct form 1, we had 4 delays. But for canonical structure, we have 2 delays for where the degree of the filter is 2. Now, we prove that the transfer function of this filter is also equal to the system introduced in equation 9.2. The governing equations of this structure are as follows. W of n is equal to 1 over a0 times x of n minus a1 w n minus 1 minus a2 w n minus 2, and the output y of n is equal to b0 times wn plus b1 wn minus 1 plus b2 wn minus 2. So we should get rid of wn to reach the original equation. But in time domain, it's difficult. So we try to use everything in z domain. Therefore, WZ will be equal to 1 over A0 times x of z minus A1z minus 1 WZ minus A2z minus 2 WZ. So we will have W of z being equal to x of z over A0 plus A1z minus 1 plus A2z minus 2. The same strategy for output. So y of z will be equal to B0 WZ plus B1z minus 1 W of z plus B2z minus 2 W of z. Therefore, y of z will be equal to x of z times B0 plus B1z minus 1 plus B2z minus 2 over A0 plus A1z minus 1 plus A2z minus 2, leading to h of z, which is equal to y of z over x of z, which is equal to the original result. So we have just proved that this structure is completely similar to the previous one. The advantage of this structure compared to direct form 1 structure is that the storage space required for it is less. Also, it has a good performance against round-off noise, which will be explained later in this chapter. The drawback of this structure is that it works poorly against internal numerical overflow, which will be investigated later again. To avoid this problem, the input can be limited by changing the scaling. On the other hand, the direct form 1 structure doesn't experience such a problem because there is only one adder in it. So, if we don't want to use scale change for overflow control, it's better to use the structure of direct form 1. Although, from the theoretical point of view, both structures are the same, but from practical point of view, they differ. Another structure, transposed direct form 1 structure. Think you see everything inside mirror, okay? And use the meaning of transpose. In the first diagram, we had x of n in the left hand side, input. So we have changed it to output. Output changed to input. Left to right, right to left, up to down, down to up. That's the strategy. Then later we see we would like to have input in the left hand side of the figure. So we have drawn this structure based on what we get from here. Okay? Just imagine x of n, x of n. Going left, going right to reach to the output, and then the rest of the story. Transposed direct form 1 structure for IIR filter degree of 2, of course, is demonstrated in figure 3. To analyze this structure, we consider the concept of transposition in its true sense. If input to output, output to input, left to right, right to left, top to bottom, and bottom to top are converted in the figure, part A will be generated, okay? Then, considering that the input should be seen on the left side and the output on the right side of the structure, all the information shown in part A will be mirrored, and as a result, part B will be created, which is intended structure. Now take home. Similar previous method prove that the transformation function of this structure is also equal to the transfer function of the direct form structure. That's the point. Now, we can similarly generate transposed direct form 2 structure as well. Okay? Without any further explanation, having mirror idea, we will reach to part B, which is our goal here. Transposed direct form to a structure for IIR filter is shown in figure 9.4. The similar analysis exists for this structure as we did for transposed direct one. Now take home. Similar to the previous method, prove that the transfer function of this structure is also equal to the transfer function of the direct form 1. Now, direct implementation of FIR filters. Due to symmetry in FIR filter coefficients, simpler structures can be considered. For an odd degree FIR filter, the following relation can be written. Y of n is equal to h of n minus 1 over 2 times x of n minus 1 over 2 plus summation k starting from 0 up to n minus 1 over 2 minus 1 h of k times x of n minus k plus minus x of n minus capital N plus k plus 1. Okay? If the filter degree is even, we can make a simplification without reading it. You see here the results. Just notice 2 plus minus. The positive sign in the above two equations is for even symmetry, and the negative sign is for odd symmetry, as explained for FIR having linear phase. We earlier mentioned 4 types of FIR filters leading to linear phase. Now we are using that idea here. Okay, here you see the structure. Very simply, it can be done. Direct form structure for FIR filter with odd degree and even and odd symmetry. Plus minus. Okay? So, that figure shows direct form structure for FIR filter with odd degree and even and odd symmetry. The difference equation is, without reading, you see any detail related. Okay? And the transfer function as well. Now, structure of FIR filter by frequency sampling method. This structure is only used for FIR filters wherein instead of the impulse response values, the desired frequency response is used to describe the filter. Let omega k be the desired frequency components. The transfer function is computed in terms of DFT coefficients, considering that the FIR impulse response, which is denoted as h of n, has capital N samples from n from 0 up to n minus 1. We have h of z. Here you see the details without reading them. Okay? Here you see the terms based on h of k, not b0 or anything related to difference equation. Any details are shown here for your later investigation. It's reminded that the values of wn to the power of minus I, where I is from 0 up to capital N minus 1, assuming n being equal to 4 is equal to the values of w based on 4 and power of 0, which is equal to 1, and w4 minus 1, which is equal to j 90 degrees, and w4 minus 2, which is equal to minus 1 180 degrees, and then last one minus 90 degrees on the unit circle. The above relations show that instead of the impulse response h of n, discrete Fourier transform values h of k are used in this structure. It should also be noted that the above structure formed for the FIR filter has a recursive form like the IIR filter. That is, the demonstrated structure has both poles and zeros. Surprise, surprise. Poles for FIR. But the resulting filter is still FIR. Why? Because the poles in W and minus K positions are removed by the same zeros locating there, by the zeros of 1 minus z to the power of minus n being equal to 0 roots. That's it. Still having FIR. To further clarify the discussion, consider the following supplementary explanations. Of course, we won't read them all. You see every details, where omega k are the desired frequency components. On the other hand, the frequency response and the DFT will be as follows. Again, without reading. As a result, the impulse response and the transfer function are equal to h of n, you see any detail, okay, and h of z, and the last part for h of z, which is equal to h1 of z times h2 of z. So, instead of h of z being described in terms of h of n, it's described in terms of frequency samples of h of k plus alpha, see Fig 9.6, where n is equal to 4. Here you see the structure, okay? Moving fast.